Hello and welcome. This is a brief introduction to the Astrophotography CAD. My name is Chris Kostanovic and I'm the founder of the Novolab Observatory. Astrophotography CAD was created for the amateur astronomers who use CCDs and CMOS imagers in their systems. It is a Windows application that allows users to better understand how their imaging system will perform, what its limits are, and which parameters to change in order to enhance the results. It does this by modeling and simulating the entire system from the target source, in other words, your star, through the atmosphere, the optics, the filter, and finally the imager. The simulation is very extensive and is carried out numerically with high granularity across the entire 350 to 1000 nanometer spectral range. So if you're looking to enhance your system or make a significant Astro purchase in the near future, you definitely want this app. It is an inexpensive way to comparison shop in an informed manner. Most of us buy stuff only to find out later that something else may have actually been better and cheaper. If you're building your own, this will help you select the correct parameters for your new system before you even start designing it. If you already have an operational system, this software will help you better select your exposure subdurations for different circumstances or reconfigure your setup for optimal performance. I'll do a lot of photometry and I use it all the time. So let's dive into the app and see how it all works. Looking at a screen, you will notice that the input parameters are located along the edges and are segregated into logical groups. So you have your sky parameters, such as your sky glow, your seeing, color of the sky, which is relatively important, not to be confused with the actual brightness of the sky, your haze, then you have your target box, which is basically your type of a star you're looking at. You can look at it by stellar class, color index, color temperature, magnitude of the star, target elevation above the horizon, and your sight altitude. On the exposure tab, you have your filter that you can select, and there is a large selection of filters that you can choose from, everything from LRGB, bandpass, long pass filters, a bunch of them photometrics, and then your exposure that you can set over here. And of course, there is an extensive collection of telescope tubes to choose from. I believe currently it's 82 and we're adding all the time. You can either even specify which optical elements you want in your telescope or in your OTA, if you will. You can change the parameters, you can save them as your own, which enables you to either modify the existing system and save it as yours or just create new one from scratch. Finally, the cameras. Just about every imaging chip that you can imagine is there, along with a bunch of cameras from participating manufacturers. Here too you can modify the parameters to suit your taste, which is important particularly for CMOS imagers where, for example, changing the gain will change the well size and the read noise and so forth. Your results will be shown mostly in a graphical form in the center panel over here. So starting with a system, you can see for your currently selected system what the limiting magnitude parameters will be for different filters, all the ones that are in your library. You can sort this by clicking on the appropriate header. You can see your system parameters, everything from simple stuff like your system F number, the effective focal length, your bend resolution, focus star size, which is essentially your the size of the star due to the seeing plus the diffraction effects of your optics. bin signal sizes, and of course the the critical focus zone and the new critical focus zone, which essentially takes seeing into account. It is a very useful parameter, and I get guided by it all the time. And finally, you know, your maximum sublet for the selected filter that you have. You can even change filters here. So if you wanted to change to this one, you would just do that, double click, and voila, it's changed up here. Limiting magnitude chart will help you determine how long you need to expose to reach a particular magnitude. So you can specify the signal to noise ratio or desired subduration. So for example, in this particular system, using the sub of only 60 seconds, in 1 hour, I can reach 22.43 magnitude. There is a brief summary here for the most common exposures. And of course, you can change the subduration to see how that would affect things. Or you can use dynamic subs, in which case the software will actually calculate the optimal subs for your systems, which are usually much longer than what you would want to use. So let's just go back to 62, make it simpler. Signal to noise ratio versus magnitude chart will show you what signal to noise ratio to expect for a particular target magnitude for a fixed total exposure. It helps you understand attainable signal to noise ratio and how subs influence it. Again, you can manually set the sub here, or you can use dynamic subs. So in this particular case, we're using dynamic subs, and you can see that signal to noise ratio changes as you increase the magnitude. It just gets lower and lower and lower. And you can see in the blue, you can see the actual exposures that are used for this, or should I say sub exposures. But if you fix the sub to, let's say, 60 seconds, now, if you notice that the range has changed, you only go down to 13 magnitude because that's when you start to saturate. And you can see what effect that has on your entire system. So going to dynamic subs, you can go down to very, very bright stars, but you know, your theoretical exposures get to be really short. Sub Explorer is a very useful chart. It shows you the signal to noise ratio for your particular target star, and you can set the magnitude over here. So I've set it up to 20, but you could dial in anything you want for a particular class star. Let me just go back to this one over here. And it also shows you the limiting magnitude up here, but it also shows you the saturation magnitudes. So as you see, as your subduration gets shorter and shorter, your saturation clearly gets lower and lower, so your dynamic range increases. This helps you determine, you know, what is the best subduration to use for your particular target. In choosing this, I find it useful sometimes to turn off the log and to look at it this way. Now you can actually see that after a particular subduration, there is very little change in the signal to noise ratio. So it really does not make sense to have these really long, you know, 600-second exposures, because, you know, you get pretty much the same results and same everything that you would with shorter exposures. But you do get to see brighter stars that are not saturated. And of course, this changes drastically if you use the off-chip binning over here. If you do that, you can see that now, because you're binning at, well, in this particular case, you're only binning at 1, so it's not going to make that much difference. But if you increase the binning to, let's say, 2, and use that, you can actually see how this changes, because now you have 4 pixels that you're reading separately and adding them up on the computer, so it's not really saturating your well. So let me turn that off. Auto binning is a very useful checkbox, because as you change your imagers and OTAs, it will set the binning for you automatically to the best sensitivity and the lowest binning that it can attain. Sampling, let me go back to this one again. You can also see a few other things. For example, here you can actually see, in addition to the usual stuff, you can actually see which is the best star and the worst, or should I say, the least sensitive stellar class, and how this is affected by your subduration. You can also see photometric accuracy. You can see the sky glow percent well, and how that changes with your subduration, and you can also see the total well. So I'll go back to this and look at the sampling. Sampling is another very interesting chart. And what it basically does, it examines how your focal reducer, or your effective focal length, or your F number, if you will affect your sensitivity. So in this particular case, we're looking at a telescope which is Astrotech 16-inch with this particular imager. And we can see that it shows the best binning for us as 2x. And it's basically saying that you will get the best sensitivity at binning of 1, or should I say the focal reducer of 1. If you notice that as you start adding focal reducers, as things get shorter and shorter, you start to get worse sensitivity. This line over here shows your Nyquist criteria, minimum Nyquist criteria. Most people think that as you make things smaller and smaller in the imager, things get better and better. This is not true. There are a bunch of parameters that are in play here, such as your read noise. So if you increase your read noise here, for example, to let's say 20, you will see how things start to change quite drastically. This little kink up here takes into account that at focal reducer 1, there is no focal reducer optics to influence anything. So you don't have any additional losses. As you add a focal reducer, that is taken into account. So this actually does make quite a bit of a difference in the whole system. Now you can look at this thing in terms of focal reducer. You can look at it as an effective focal length, or you can look at it as just the F number. You see down here there is a small short summary telling you how this is reached. These numbers are reached. You can also see your diagonal in terms of arc minutes, and you can see your field of view at the current settings. You can change things. You can change your sub to, I don't know, let's say 120 seconds. And you can see how they will influence things. You can either decide that you want to observe this thing at a different signal to noise ratio. So let's say I want to do a signal to noise ratio of 15. Oops, that's not good. And you can see how everything will be affected. So let me just reset this. You can also look at the signal to noise ratio as opposed to limiting magnitude. Now this is something that was unexpected to me. And what I found out is that actually the signal to noise ratio is influenced very heavily by the magnitude of the star. So as you go towards brighter stars, you can actually see that you get the best signal to noise ratio at a very different focal reducer, or very different effective focal length. As you increase the target magnitude, it starts to look pretty much like, guess what? Limiting magnitude. So that was an unexpected thing for me. So system response page is at the root of how the software works. It lets you examine in more intimate detail how your system operates. If you ever wondered how a particular item affects the light throughput in your system, well, wonder no more. So you have the ability here to see your target flux, your optics, transmission parameters, your filter. Well, we're not using anything now, but I don't know, let's say we want to use, well, my favorite is Astrodon. So I'll use Astrodon. So these the filter, your CCD response, your extinction, and that is going to change with target elevation. So if your target elevation goes down, you can actually see how that affects it. At 90 degrees, it's going to be, the best that you can get for your site. Your altitude, your haze, on the hazy day in the summer, you're not going to have the same transmission that you do. So all these things are taken into account to calculate the extinction. You can also see the total overall system quantum efficiency and target throughput. So for example, in this particular case, as we change if we change for example, the star to A, you clearly see there's a different input flux, and the amount of photons, the number of photons that hit your CCD correspondingly decreases. The sky flux is basically the density of the light coming from your background sky. And that is going to depend on where you are. It is essentially photochromaticity of the sky. So if you're in a rural dark area, it is pretty much flat. There's very little there. If you're in a typical suburb, you're going to have some of the LED stuff and some of the high pressure sodium. But some people live in suburbs that are mostly LED. Some people live in suburbs that are mostly high pressure sodium. And then some poor souls live in urban areas. Now, this, again, is not to be confused with the actual brightness of the sky. This is really just the color of the sky. So up here, you have a couple of other parameters, equivalent aperture. So in this particular system, we're using a 16-inch telescope, but it is really, with this camera and everything, it is really behaving as a system that has 130 millimeter diameter of the optics, because its quantum efficiency in this setting is only 13%. Let's take out the filter and see what it's like natively. So natively, it is actually, with this camera, it is at 51% quantum efficiency for the entire system, everything, excluding the extinction. With the extinction, obviously it is a little more. So, we go from equivalent aperture of 258, and that will be 258 in a perfect telescope with a perfect imager. And of course, the quantum efficiency of 51.7% means your system really has a loss of 0.72 magnitudes. Filter evaluation page is yet another page that is very interesting. It looks at every filter that's in a library, and it calculates the equivalent exposure multiplier that you will need in order to attain the equivalent either signal to noise ratio or the light grasp. So we have here an A0. So let's look at the O2 star. So it's something really, really blue. So you can actually see that in this particular case, you have the shortest exposure with no filter, obviously. And if you float above it, it will tell you what your exposure multiplier is. So if you're taking an LRGB image, it will tell you that to get the equivalent signal to noise ratio for each filter, how long you have to multiply with respect to this. I typically like to use the signal to noise ratio rather than the light grasp, but there's different applications. Different people will do different things. There is also, on this side, we have a second chart. We have something I call exposure quality index. So in other words, looking at your signal to noise ratio with respect to the background sky glow, and looking at how long your exposure is going to be to attain the same signal to noise ratio. Using those two parameters, you can kind of come up with a factor that tells you, okay, which of these combinations is going to be the best for me. In other words, give me the best signal to noise ratio at the shortest exposure. So let's take a look at a really interesting example. Let's say that we're looking at a really, really cool star that's very red. So now, if you look at this, you can actually see that there are some filters that, if you look, for example, at the down here, the 610 nanometer long pass, you can see actually the exposure is pretty much the same as it is. Actually, it's better than with no filter. And correspondingly, you can actually look at the exposure quality indexes. You can select which of these filters would be the best for you. There is also other things that you can look at: combined system efficiency, signal to noise sky glow ratio, and another one that's very interesting is the filter attenuation. So for this particular star, you can actually see that what is the actual attenuations with respect to the best there is. So in other words, this particular filter will give you a signal to noise ratio of whatever it happens to be, but it has actually, compared to it, no filter will actually be worse. It will attenuate by 0.2 mag. It's kind of hard to grasp, but it's basically the way the stuff works. Let's go to the imagers. So here's a library of all the imaging chips and cameras. And there's going to be more added shortly in terms of cameras. These are just chips right now. And you can see for every one of these, you can see what type it is, the size of the pixels, the average quantum efficiency, which is the quantum efficiency, not the peak, it's average quantum efficiency from 350 to 1000 nanometers. Because our objects are not just at the peak quantum efficiency. You can have a very sharp peak and it can be an absolute bummer down in the infrared. So this kind of gives you a measure across the whole range. Your well depth, your read noise, dark current, and then you can see your pixel resolution of the imager. But at the same time, in this particular system, you can actually see what the field of view would be. And then the optimal binning in this particular system, the focal reducer to reach it, diagonal of the chip in the millimeters, which is important when you consider things such as how flat your field is and how big of an imager you can have before you start to get really weird results. You can click on this little thing over here again to change it to the diagonal in your system in terms of arc minutes. And then you have over here a system 1 hour limiting magnitude. So this is the 1 hour limiting magnitude in this particular case with no filter. You can of course change that. If you click on this, you also get the theoretically best in your system. You can click on any of these to sort them out in ascending or descending order. So in this particular case, you can see that the best performer in my system would be Perfecta 20K, which is a perfect camera with zero read noise and huge well, and it's a theoretical camera that I came up with. It just essentially gives you an idea of what is the best that your system could do. There's no way the your system could do better than 22.76 in this particular case. But you can actually see, the imager that you're currently using, which is in red. You can see what it can do, and you can then decide, do I need to upgrade to something different? Is it worth it? Sometimes you get a better sensitivity, but your field of view is not as good. And then, of course, your OTAs, a very similar approach in this one. You have your aperture, focal length, f number, different parameters. Average of transmission is pretty much the same like the quantum efficiency for the imager, but this is for the OTA. So, for example, your optical tube will have an average transmission of 82% all these. And the reason why it's the same is because it's essentially they're the same materials, the same construction. And so you can look at it and you can find out, hey, if I have a very old Celestron that has a star bright, well, that thing has, only 59% transmission. But if I went to the newer stuff with the Edge or XLT, it's 73%. So you can look at The very old Meade telescopes, with the EMC coating, actually they only have 35% average transmission across the entire range. That's including the both mirrors and the corrector plate. Equivalent area is essentially what would be the area of a perfect telescope that would be necessary to accomplish the same light gathering effect that this telescope has. That's another way to look at the average transmission in your system, but now combined with the size of the telescope. And of course, any of these you can sort them out, and of course you're going to see that the best limiting magnitude as well as the equivalent area is going to be something like a 24-inch plane wave telescope. You can of course look at that, but you can also look at it in terms of what is what I call a OTA 1 hour index. In other words, if you had a perfect camera looking at something that's a zenith, I believe it's a K0 star, what is it that you could achieve in 1 hour? And it's a good way to compare just the OTA without any effects of the imager. So this is just an OTA parameter essentially. So this way you can kind of look at how they compare. Well, when you look at these things, you see that there are a few other little features. So let's change the filter over here. And now you notice that there's this little icon over here that has a link. And you will find that if you in some of the imagers also. If you click on this link, if it's lit up, that is, it will take you to the website of a participating manufacturer. So in this particular case, wow, taking a long time to load. Of course, it's coming from Germany. You can actually get much more detail from this than you would just over here. So, or you can just go and buy it over there. The same thing is for the OTAs and same thing for the imagers. These links over here will take you to the place that's appropriate for you. So if you live in Australia, it's not going to take you to the US distributor or US website. It's going to take you to a local website. If you're in Europe, it will be the same, and they will take you to participating manufacturers and participating distributors. A few other little details. There are easy ways to set up. So, for example, in minutes, you could type over here, I don't know, 4.52 minutes, and it will come up and will convert the whole thing. But in order for you to go back to, I don't know, 2 minutes, there's a whole bunch of change you need to do. So if you just click on one and change it to 2 over here, there you go. Up in this upper left-hand corner, you will see a couple of icons. You can change settings over here. Whether you want to show tooltips or not, there are very extensive tooltips which I've turned off because I really don't need them. You can restore your OTA to default, change or import your license, and you can see what's in the library right now. There is also this question mark over here, which if you click on that, it will open up on the different screen for me, but it will open up a built-in PDF browser, so you can actually go and read the manual and find out about how to do different things. Finally, the software will look for an update every time you start it, and if you choose to do so, it will update itself. It doesn't take very long. It's fully automatic. You don't need to go to any website. And it's an important thing to do because as the time goes on, new features are being added, as well as new devices, new OTAs, new filters. So now that we've gone through the basics of the operation of this, let's take a look at a couple of or few use examples. So I have an old CGEM mount, and I wanted to convert it to I don't know, supernova search. I happen to have a couple of interesting lenses that I want to use for this specific application. Clearly, I do have some parameters in mind. I want to be able to see somewhere to detect between 17 and 18 magnitude. I want to be able to do this while I'm shooting at least 1 square degree per minute. So let's see what we can do. So I have added these couple of lenses in here. So I'm just going to go down here and I'm going to look at this wide field refractor, which is a really interesting lens. It's a very, very fast lens. And I'm just going to use I have a couple of old Santa Barbara cameras with CAF 8300, so I'm going to use that. I'm going to auto set the binning, and I'm going to take a look at see what it looks like. Oops, well, I'm way down where I don't belong. Let's change this to 1 minute, and I can see that clearly I need to make some changes over here. This is not going to work. So one other thing I should note, that signal to noise ratio of 3 is great, but for me, I'm not really that good at detecting that just by quickly glancing at stuff. So I'm just going to say, let's say signal to noise ratio of 8 is what I need. And of course, we're looking at supernova, so that's going to be different class star. I'm going to be looking at it with no filter. What else? Yeah, typical of seeing everything is about right. So clearly, in order for this thing to work, I do need to put some kind of folklore reducer. In my particular case, actually Barlow, so it says 2.75 is kind of optimal for me. So let me go with 2.75. And I see that at that particular one, I have 3.73 degrees, square degrees per frame. So I'm just going to change my exposure to 3.73 so that I'm getting the appropriate exposure. Remember I said 60 seconds per 1 square degree, and I'm going to make the my exposure max because I don't want to be doing a whole bunch of binning. So now I'm looking at it, and the best that I can reach is about 16.9. So that's not really kind of where I want to be. I thought this was going to be better. So let's take a look at this other guy that I have. It's a bigger lens. It's a 5-inch lens. Now in this particular case, we can actually see that I actually have 2.84 degrees view, so I'm gonna just change this to 2.8. And now I can actually see that, all right, I can reach 17.3. So this would actually satisfy what I want to do for this particular imager and this particular signal to noise ratio. Let's take a look at another example. Let's say that you have I don't know, let's see, let's take a pick. You have an old Celestron C11 star bright. And I actually used to use that OTA a long time ago. And I remember my folklore reducer would bring it down to 0.73. And I was using CAF 8300 in those days. So this is basically what I was getting. So in other words, 1 hour exposure. Oops, that's not what I meant to do. And we have to do this. I was able to see down to 21 or so. But now time has passed, and the telescope is not new anymore. So let's take that into account, because mirrors do degrade over a period of time. So let's just assume that they've degraded to, I don't know, 90% of their original reflectivity. 2 mirrors, so 0.9 by times 0.9 is 81%. So I'm just going to put that 81%. So now I'm actually seeing that what I can see, the best I can see for this type star. And let's change the type of a star to, I don't know, G, just to give us an idea. That is the best that I could do. So let's see if we can And of course, look at my field of view is 30 by 22 basically. So let's see, what kind of a camera can I use that would give me something better, and is it worth spending the extra money? So let's take a look at the imagers over here. So in my particular system, which is going to be done here, and let's do the sorting. So now it's sorted in descending order. Well, actually, we want to do it in this way. So it's down here. Now, there are many cameras nowadays that will do much better than that. But the secret is I'm actually interested in having my diagonal to be pretty much the same. So, 37 or whatever arc minutes. So there are different cameras, some very expensive. But if you look at it over here, probably a good choice would be something like this, a little more, and gives me 21.66 as opposed to 21. So, in other words, about 0.3 more. So let's switch over to that and take a look at the sampling now. In this particular case, and let's change this. And now you're looking at it. If I just looked at it natively without any focal reducers, that's less than what I had before. I can go to 0.73 again. It's the same system. Yeah, I actually have improved a little bit, went from 0.83 square degrees to 1.1. So, but I do get better sensitivity. I've gone up, if I recall correctly, about half a magnitude, which is not negligible. That's actually pretty good. So let's take a look at another case. Let's leave this image as it is. So let's look at the OTAs. So in this particular case, I'm using the Celestron C11 Starbright. And in my particular case, today, what do we say, 81%? So this is pretty much what I'm getting now. So it's, 21.6 limiting magnitude at this particular focal reducer. Let's see what we can do. See if there's any other OTAs that we can do. Actually, before we do that, let's try something else. Would it be worthwhile to spend a couple of $100 and have my mirrors recoated? Let's take a look at that. So right now, I'm at 21.657. Let's say I had my mirrors recoated to the way they were when I bought stuff. It went up, but hardly at all. But what if I put enhanced coating on it? Right now, we're seeing a little bit of a change. What if I decided that, enhanced coating, I would have to, you can change the coatings. And if you look at it, you have different types of mirrors. We're going to be doing aluminum mirrors, so it's going to be protected, enhanced aluminum. So that's type 2. So we're going to put 2 over here, because it's no longer a Celestron mirror. Now it has gone up quite a bit because we made it enhanced. What if we chose to do silver? Silver was 3. So we went up 0.3 magnitudes, which for a couple of $100, that's actually not bad, It's certainly worth the money as opposed to buying a new OTA. However, if you were looking at a new OTA, and let's restore these parameters to the way they were. So if you're looking at a new one, and in this particular case, this one is right now at 80%, let's say. So we can actually see that there are obviously a bunch of optical tubes that will do better. I forgot to mention some of these optical tubes or some of these telescopes are actually in kind of reddish color. They're refractors. The blue ones are all reflectors. They're all mirrors. So in this particular case, the best that we can hope to do with this telescope is 21.86. But if you go and look at some other stuff over here, you can take a look at, for example, at, let's say that we went to the C11 edge. Yeah, you can see that it's actually better, but really not a huge difference. I mean, realistically speaking, it's really not worth getting it just for the extra sensitivity. Your field will be very flat, and you will not have to use a reducer or corrector to flatten your field, but you're not going to see much more. However, if you look at some other stuff, like for example, look at the Astrotech 12-inch. I'm trying to stay within the same money kind of thing. You can see that some of these, like for example, the 12-inch Quattro or this 12-inch Newtonian, which is f4, actually is a significant difference between these two. And taking in mind that this is without me losing 80% of the light because it's an old scope, yeah, that would be definitely worthwhile. So if you click on this, you can actually change the Quattro, and so you can go and buy your C11 Edge for, I don't know, $4,500, I think. But if you go to Quattro, not that I'm proponents of Quattro or Newtonians, I'm just making a comparison in terms of performance and money. You click on this, and now you take a look at it, and you can see, well, this thing is only $1,800. Add another, $200-300 for the corrector, and it doesn't look bad at all. So this is yet another way that you can look at stuff, how you can decide which way you might want to go. So let's take a look at something else. Let's see how we can choose which would be the best filter for doing things. So let's say that we're looking at some kind of a carbon star or something really red that's not that easy to see. And we want to optimize our system for this. So if you look at there's various ways to look at. You can look at a filter evaluation. Take a look at the exposure index. You'll find out that something like this gives you actually best performance. And if you look at it, the exposure multipliers for all these things are pretty much nothing. So it's like like you don't have a filter essentially. So from that point of view, it would say that your 610 long pass will be optimal for you. So let's take a look and see if that's really true. So take a look at sampling. We're going to change the filter to what do we say? 710, 610. Sorry. All right. So for this particular imager, and it looks like it's 21.5. Another way to look at it, we can go down here and sort them out. Oops, sorry. And yep, the one that we selected right now is the best one, followed by a few others. So you can go to Astrodon blue blocking with almost identical results, but really this is probably the cheapest solution for this application, and a lot of people actually happen to have that. Same thing can be applied for different situations. You will usually get that, but do bear in mind that if you do have any blue stars in that field of view, that they're not going to be equally treated. This would be good if you're trying to, for example, measure a magnitude of a star for photometry or something of that kind. All right, finally, let's just look at quickly at the setting up the sub duration. So we're going to take a look at a sub explorer. We're going to, I don't know, select a G star in this particular case, and let's say that it has a magnitude of, I don't know, 19.6. At this particular elevation, not that it matters really that much in this particular case, but so this is what we're looking at now. And we're trying to choose the best sub duration. Now, clearly, we want to have always the best signal to noise ratio, no matter what we do. And you can actually see as your sub duration increases, you can see that the signal to noise ratio also increases. And it keeps on going all the way up to your maximum sub duration, which this particular case is 3600 seconds or 1 hour, because it doesn't saturate the imagery yet. But you know, who wants to take such a long exposure? In reality, you know, you want to have shorter exposures, because likelihood of, you know, a plane passing through or something going wrong is much better if you have a short exposures. But you can actually see that there is not a whole lot of change over here once you get beyond certain sub. And the best way to see this actually is if you turn off the log. Look at it this way. And now you can actually see that once you get past, I don't know, 120 seconds, there is hardly any change. So, you know, whether it's 120 seconds or, you know, 180 seconds, you know, take your pick. But this is a really simple way to do this. And at the same time, let's say that we fix it to 120 seconds. This is probably an easier way to look at it this way. So we had 120 seconds here. You can actually see that your saturation magnitude is 12.6. Whereas if you had something that was much longer, you know, now you get to saturate starts much earlier. If you want to have if you have a really diverse stellar field and you don't really have any dim stars in there, you may actually want to reduce your sub duration so that you actually have more stars that are not saturated. So yeah, you will have more subs, but so let's say that if you're looking at 20 seconds, you can look at it also in terms of number of subs. That's another way that you can look at stuff to help you determine what you want to do. So in brief, this is roughly how you would use the Astrophotography CAD, what you can do with it, its features. I hope that this presentation has helped you better understand it, its use and operation. I will have more extensive tutorials on its use along with some more real-world use examples. Until then, thank you very much for your time and attention. Goodbye and clear skies.